Hey guys, welcome back. Today we're doing angle sums and differences. Now in this video I won't actually be doing any proofs of the formulas that I'll be doing for sums and differences, which I have down here. We'll go through in a second. This will be solely focused on the examples of problems that you might get in this topic or this section. Before we get into the actual sums and differences of angles, I'd like to quickly go over some trig identities that you may or may not be aware of. Okay, your tan theta is sine theta on cos theta. That one should be one that we're using regularly. These other three, though, might not be. Okay, sine squared theta. Now, when we write squares, we put them above it. This means that it's sine of theta all squared. Okay, so as an aside, here we've got sine of theta all squared, like this. Instead of writing it, we write the square in the middle so as to not confuse it with the angle squared. Okay, so sine squared theta plus cos squared theta is equal to 1. You'll notice in the unit circle, cos is your x, sine is your y in a 90-degree angle triangle inside the unit circle here, and you have a hypotenuse of 1. This here is just Pythagoras' theorem. You could put a square on here, but 1 squared is just 1. So cos squared, bottom of my triangle, plus sine squared of this angle is equal to the hypotenuse 1. These other two, sine and cos, are quite closely related because you're thinking of this angle here where we've defined sine and cos previously. If you think about the opposite angle, or the other angle here in our 90-degree angle triangle, this is 90 degrees, or pi on 2 radians. Take the angle, okay? And then you'll notice that from this angle, opposite over adjacent is cos theta over 1, or just cos theta. And then same situation with cos. The adjacent to this angle is now sine theta, so this will be sine theta over 1, which is just sine theta. So these are some trig identities that we need to go over. Alright, sums and differences of angles. So we have quite a few formulas here. We've got 6, 2 for sine, 2 for cos, 2 for tan, where they are adding or subtracting. So you've got your angle sums and then your angle differences for each of your trig functions. Sine and cos looks a little bit different, alright, but there's a pattern that you might see emerge a little bit. What I like to think about is that for sine, the sign, positive or negative, does not change. X plus y means that you're adding both of these things, but the functions themselves change. So it's not sine sine cos cos like it is in the cos sum and difference formulas. Alright, so sines don't change, but functions do. Cos functions don't change, but plus becomes a negative and the negative becomes a plus. And tan's a little bit wackier, but going over it a little bit, a few times using it, will get you into a plus on top when there's a plus here, minus on the bottom, minus on the top, plus on the bottom. So the top matches the sign, whereas the bottom does not. And we'll use it a couple times and you'll get a little bit more used to it. But there is a little bit of a way to remember sine and cos formulas. Anyways, let's use these before I run out of time here. We have expand cos of 3a plus 2b. So we're using the sum of two angles here for a cos function. So it's going to follow this formula here. We're going to have cos of, and you can kind of think about this first part as x and this second part as y. Alright, so cos of x, which is 3a, I'm following this up here, cos of 3a times by cos of 2b. Take sine changes for cos. Then we're going to do sine twice. Sine 3a sine 2b. And so just replacing my x and y's that I had in my formulas with what it goes in place of x and y in the example. All right. Tan alpha take pi on 7. Okay. This is going to be equal to, this is my x, this is my y. All right, and I'm taking, so it's going to be tan of alpha take tan of pi on 7 over 1 add sign changes on the bottom line, tan of alpha tan of pi on 7. That's all it's required for expanding. Follow the steps and you can rewrite the whole formula first and then replace your x and y's with the appropriate parts in the example. Okay, let's try and go back the other way. We take something that looks like one of our equations and then we want to go backwards to the sum or angle formulas. So here we've got cos of 2p, cos of 5q plus sine of 2p times by sine of 5q. Okay, so the functions aren't changing. Which formula does that mean we're using? The functions aren't changing, so we're looking at cos. But there's a plus in the middle of these two, so we're going to have to do the difference of these two things. So it's going to look like cos of 2p take 5q. Just like that. Okay. Cos the functions don't change, the signs do. Now the angle sum and difference formulas still work for any angles, whether they're degrees or radians. So we can do something like this, just like we had before. The functions are changing, so this time we're doing sine, but the sine does not change. So we're going to do 54 degrees take 33 degrees. And because we know what that can simplify to, or we can work that out, it's the same as sine of 21. This next one's a little bit trickier. Okay, trying to simplify this situation requires a few different steps here. Let's think about this cos of 2x. Alright, cos of 2x is the same as cos of x add x. And I'm going to have to try and squeeze this in because I'm not sure I've given myself enough room. But cos of x plus x is equal to, for your cos function, we're doing the sum of two angles here. Cos function, the functions don't change, but the signs do. So I'm going to do cos x times by cos x. Oops. Take sine of x, sine of x. Oh, that's getting very curious. Let's just write it like this. Cos 2x is equal to cos x times by cos x is cos squared x. Take sine x times by, and I know you can't see it now, but that's also sine x. Sine squared x. Okay, so now we're going to substitute this in place of cos of 2x. And I get cos squared x, take sine squared x, add 2 sine squared x. Okay, so this is going from here to here. This is a little aside part, these next two lines. So sine squared x plus 2 sine squared x are like terms, so we can put these together and we get cos squared x plus sine squared x. And you might remember that cos squared and sine squared of the same angle added together is the same as 1. Right. This is a double angle formula, which you will probably find somewhere in the exercise that you'll be doing. Alright, now before we continue to the next couple of examples, we can use these sums and difference angles to find exact angles for other angles. So, for example, we could do 15 or 75 or 105 from the angle and exact values that we know. So we know exact values for 45, 30, and 60, and we can find other angles based on those using the exact values that we've done in previous videos and our angle sum and difference formulas. Let's give it a shot. Okay, example 3, find the exact value of sine of pi on 12. Now you'll notice that I did the radians here as well. Alright, pi on 12 is pi on 4 plus pi on 6, or you might like to convert it to degrees. In fact, I might do that for simplicity. It's the same as sine of 15 degrees. Little degrees sine, sorry I've written that so small. And we're doing sine of 45 take 30 degrees. Okay, which means we're going to have an add in the middle. Let's go sine of 45 degrees take 30 degrees equal to add's going to be in the middle because the sign changes, but it's going to be sine 45 cos of 30, and then cos 45 sine 30. And we know the exact values for each of these. Or we can go back to our tables and look. So sine 45 is 1 on root 2. Cos 30. Cos 30. Occasionally your sketches of your triangles can help. So I'm using 1 now. Cos of 30 is root 3 on 2. Cos of 45 is 1 on root 2. And sine of 30 is half. Alright. Now, because they're different denominators, it's going to take a little bit of time to go from there. But running short on time, I'll let you guys take it from there. We've used the angle sum and difference formulas and then replaced our angles of angles that we know with exact values. Alright. You can do a similar thing with tan of 7 pi, which again, 7 pi on 12, sorry. 7 pi on 12 is 105 degrees, which is 45 and 60. So 45 degrees and 60. And so you would need to use the sum formula for tan and then replace the exact values that you could find from there. Alright. Last style of quadratic example that we'll do for today. Okay, this one takes a little bit longer, so I might have to rush a little bit, trying to keep to that 15-minute time. Find the exact value of sine A take B if sine of A is 5 on 7, cos of B is 3/5, and A and B are both in the first quadrant. This first quadrant information is very important because when we do figure out, basically what you'll see is when we expand sine of A take B using our angle difference formula, you have sine A cos B, which we know the values of, but then you're going to have take cos A and sine B, which we don't. You might have had this question or this type of question in a previous exercise, but we need to use right angle triangles of these angles and then pay attention to whether they're in the correct quadrant or what quadrant they're in order to tell whether they're positive or negative. So let's look at this triangle. We have sine of A is opposite 5/7 hypotenuse. Okay, and then with some Pythagoras we can work out that this is root 24. 49 take 25. And that means that cos of A is root 24 on 7. Guess I've given myself very little room. Anyway, similar idea here. Pythagoras to find out the other edge, and then we can find out that sine of B is opposite over adjacent. Oh, sorry, not opposite over adjacent, opposite over hypotenuse. And then we can find out and replace each of these. So sine of A is 5/7. Okay. Cos of B is 3/5. Take cos of A, which is root 24 on 7, and sine of B, which is 4/5. At that stage, I'd probably use a calculator, which I'm sure I can let you guys do. And that's the end of our examples for today. All right. I think that's it. Let me know if you need a hand.